Hello, this is Lab 1 for Physics 2212. Introduction. So the purpose of this lab was to prepare charge tape and then observe its interaction with another piece of charge tape and experiment to find out how much excess charge is on one piece of charge tape. Then we're going to compare those results to a computational model that should calculate the charge required for this observation by treating the system as a point charge. Models and fundamental principles would be Newton's second law, F equals ma, the force due to gravity, F equals mg, and Coulomb's law. And a brief preview of the result will be we find the charge tape was positively charged and it was electron deficient and it had a ratio of 1 electron for every 6.13 times 10 to the 6 atoms. So the main physics ideas and models involved. First, we have Newton's second law, or force equals mass times acceleration. In this case, we're just going to look at the force due to gravitational acceleration, F equals mg, where g is 9.81 meters per second squared. Also, Coulomb's law. So according to Coulomb's law, the electrostatic force should be K, or 1 over 4 pi epsilon naught, which is equal to 9 times 10 to the ninth. I'll multiply that by both charges, and then we're going to divide that by the square of the distance between them. That's important because the bigger the distance is, the smaller the electrostatic force will get because it varies inversely to the square of the distance. Also important to note is that like charges will repel each other and opposite charges will attract each other, so that can be helpful to figure out the sign of one charge if we know the sign of the other charge. So for our model, we're going to take a piece of charge tape and place it on both ends so it's free in the middle, and then bring another piece of charge tape up to it so that it is repelled by each other, since they should have the same charge. Okay, reasonings. So from the second law, we know that if there's no net acceleration, the net force should be 0. And we know this because after you bring tape A up to B, the tape should stop moving. So the force from gravity and the electrostatic force should cancel out. And using this assumption, we can calculate the number of electrons. So in this case, the system is tape B. The surroundings would be the universe around tape B and tape A. Also, for initial conditions, we're going to say tape B is at rest with only gravity acting on it. And we're going to assume that the tapes can be treated like point charges. Both tapes, which in our assumption is identical in size and mass, and which is why we will give them the same exact charge when after you perform the charging process. And we're also going to assume that the charges are evenly distributed across the surface of the tape. Okay, so for the experiment, we put one piece of tape sticky side down on the table and another piece of tape sticky side down on top of that. Then we quickly pulled the first piece of tape off, which would effectively charge it. And we observed that this piece of tape had a positive charge because it was attracted to a negatively charged pen, and opposites attract. We also observed that when we placed the charge to tape B on two ends and brought the charge tape A to the first, B was repelled and it moved up by 0.025 meters. So for our calculations, we found the mass of the tape using the density that was given to us of 1 gram per meter, and using the length too. So using that, we found the mass, and then using the mass, we need it for Fg. So we say the net force is equal to 0, which means that Fe minus Mg should be 0. And then we plug in the values in the formulas that I discussed in the previous slides. And here is Fg's value, and then here's the electrostatic force. And again, we're going to assume that both tapes have the same charge, which is why we're using Q squared. So then we're going to find Q, and then we're going to use Q to find the number of electrons lost by the tape, because you should be dividing the charge of a tape by the charge of an electron. So this is the amount of electrons that were lost. So to find the number of atoms on the tape, we can just divide the area of the tape by the area of the atom, and then to find the ratio of electrons to atoms, we can just divide them over each other. So for our code, I set it up similarly. So first I have my constants listed, then here we calculate Fg, and then we say that the electrostatic force should be equal to Fg, and then we solve for Q using Coulomb's law. And then here we're printing out the charge to find the electron count. We're dividing Q by the number of electrons. Then we're also finding the ratio of atom to electrons. And then this is about the visuals of the tape. So the orange is tape B, and the green arrow is the force from gravity, and the up arrow is the electrostatic force. Discussion. So the similarities between the two models would be that the excess charge, deficiency of electrons, and ratio of electrons to the atoms were very similar, where they had the same magnitudes, and the actual numbers were very same if you look back at the past slides. Some possible sources of error would be that we could have measured the tape length inaccurately. This would impact the calculated mass and area and affect the gravitational force, which would therefore would affect the electrostatic force calculation. The area would also change the number of atoms. Also, it was difficult to measure the distance that the tape rose up, and this would affect our formula for electrostatic force since it's inversely proportional to the square of the distance. So in conclusion, so the electron deficiency was 8.16 times 10 to the 10 electrons. But what if electrons had a positive charge and protons had a negative charge? what would change. So none of the observation would change because opposites would still attract each other and likes would still repel each other. Just this time, the tape would be negatively charged, and the plastic pen that we did in the beginning would have been positively charged. But other than that, the values of like the distances should still be the same. Why is it important to handle charged tapes as little as possible? This is because as the tape touches other objects, electrons are transferred to the other surfaces. So with more interactions, it would lose charge and decrease the electrostatic forces. And after a certain amount of interactions, it's hard to assume that the two charges or that the two tapes still have the same charge, which would make our formula a lot more difficult.